Now we talk about irreversibility and heat generation in the computing process. It is argued that computing machines inevitably involve devices which perform logical functions that do not have a single valued inverse. This logical irreversibility is associated with irreversibility and requires a minimal heat generation per machine cycle, typically of the order of kT for each irreversible function. Classification of the data processing equipment that we have. We classify the data processing equipment into three types. The first class and simplest class consists of device which can hold information without dissipation energy. Ferrites and thin magnetic films comes under this class. Consider the function restore to 1, which leaves the particle in one state regardless of its initial location. If we are told the particle is in the one state, then it is easy to leave it in the one state without spending energy. If the particle is in some other states, then we can apply force to it, which will push it over the barrier where when it has passed the maximum, we can apply a retarding force. So when the particles arrives at one, it will have no excess kinetic energy. Now we discuss about chirotrons. Chirotrons are devices which show dissipation only when switching. The preservation of information depends on the fact that Brownian motion in the box is very low. There are two states in the box which are not separated by the barrier. Computers can be built that contain only chirotrons or only magnetic cores. On your right, you can see two diagrams which represents by stable potential well and a potential well in which state 0 and 1 aren't separated by a barrier. Second class of devices are those which consist of structures which are in steady state but in a dissipative one when holding onto information. Electron flip-flop circuit relays and tunnel diodes comes under this class. All active bistable devices have built-in means for restoration to the desired slab. In the case of dissipative device, there will be transitions from the desired state to the other stable state, resulting from thermal agitation or quantum mechanical tunneling. Only one of the two possible states for the negative resistance device, only one is really stable and the other is not really stable, that is, it is metastable. In general, when using such devices in computing circuits, one tries hard to make the dissipation of the two electric states small by pushing their states as closely as possible to the voltage or the current axis. Our intuitive explanation is that in the steady state dissipative device, the dissipation per switching event is at least as high as in the device of the first class, and that this dissipation per switching event is supplemented by the steady state dissipation. We move on to the third class of devices, which is called catch-all, namely those devices where time variation is essential to the recognition of information. This includes delay times and also carrier schemes, such as the phase bistable system of Newman. The von Neumann architecture describes a design architecture of a computer consisting of a processing unit (ALU) plus processing registers, a control unit, a memory to store both IR and data, external mass storage, and I/O mechanisms. There is power dissipation in this kind of devices. Now we move on to irreversibility. We call a device logically irreversible if the output of a device does not uniquely define the inputs. Logical irreversibility, we believe, in turn implies physical irreversibility, and the latter is accompanied by dissipative effects. The second level of argument considers a particular class of computer, namely those using logical functions of only one or two variants. After a machine cycle, each of our n binary elements is a function of the state of almost two of the binary elements before the machine cycle, taking case 1. Now assume that computer is logically irreversible. The machine cycle maps the 2 power n possible initial states of the machine onto some same space of 2 power n states, rather than just a subspace thereof. In 2 power n possible states, each bit has a 1 and a 0 appearing with equal frequency. The third level of argument we permit more general devices. Let PQR be the variables before the machine cycle. The variables PQ are left unchanged during the machine cycle. In this operation, R is the choice of input and PQ are operated upon. The computer should save enough of the input information so that it supplements the desired result to allow reversibility. Every time a truth function of variables is evaluated, we must have some additional information about the quantity being operated on, whether we need it or not. If our machine is capable, as machines are generally understood to be, of a non-terminating program, then it is clear that the capacity for preserving all the information about all the intermediate steps can be there. Our unwieldy machine has therefore avoided the irreversible operations during the running of the program only at the expense of added comparable irreversibility during the loading of a program. Thank you.